Oh, for the recording. Okay. Hey, so I will take just one thing. Should take with a grain of salt. It's not my project. It's a project of the community, and I think this is kind of what I'm trying to convey today. There's not actually going to be a lot of placing of people on the map. There's a few people. Some of them are here, but the idea is to present a project that is an ongoing project that hopefully involves all of you, as well as the people who call themselves organizers, including myself. But the idea, like I said, or didn't, is to create a dynamic living map of the Israeli ecosystem, everything that's happening, both in academia as well as the industry as it's growing in government. I will say one more thing. We've been discussing the differences between I would say it's different areas of quantum technology, quantum computing, quantum sensing, quantum communication, networks, and we felt like we should try and be as inclusive as possible, especially now that there's not a lot of stuff going around and everything's important and everything is kind of influencing everything else, which actually makes drawing the map a little harder. So it's not just quantum computing proper, but this would include quantum communication, quantum sensing, etc. The idea behind the map, obviously understanding and kind of realizing what's happening, but ultimately we want to promote cooperation. We want to kind of nurture innovation where it's needed and make the connections. And like I said, this is FUBU. This is for the community, by the community. So I'm not sure that you're aware of it, but by coming here and sitting down, you volunteered. So thank you for volunteering, and we expect to see results very quickly. I just go very quickly over how we're kind of doing this or how we started doing this. So the first thing is having discussions, right? So talking to people, whether it's in academia or industry or government, but kind of getting a personal approach. Hey, Alicia, getting a personal approach and understanding kind of what the people do, and then bringing this back into a centralized database where we can collect it and then work on, you know, organizing it, categorizing it, tagging it. And like I said before, I keep saying it's a collaborative effort. We are going to have all this information available online, and hopefully we will have not just a way to go and view this, but we will also have a way for people to come and participate and add more information and improve on tagging, et cetera, et cetera, et cetera. Again, hopefully soon, maybe a few weeks, we have a volunteer, a specific volunteer for that. So hopefully that will happen quickly. So I want to take whatever time I have left. I really want to do this as quickly as possible, but I want to talk to you about you know, how we structured or how we went about creating an initial structure for the map and kind of placing some data on it. So there's two things. One is a map is two-dimensional usually, so that means 2 dimensions. So which dimensions do we choose for a grid for the map? Obviously, when this is online and this is being worked on, there are many more dimensions. The dimensions that we didn't do, location, you know, where the places are located, the physical mechanisms used for the technology. And again, I'm probably going to talk about this in a little bit, but it's not as a dimension of the map. The maturity of the project, where the project is, it an academic project or a research project or industry. So all these were left out, and we chose for this map that you're going to see today, we chose 2 dimensions. One is the paradigm. I'll go a little bit over what paradigms we kind of divided into, but the paradigm is, like I said, quantum sensing is, let's say, a paradigm, we'll see. And the other is layers, you know, hardware, software, algorithms, same layers that at least I know and like from a classic software engineering world. So this felt like a good way to start looking at the data and start separating it. And like I said, as we move forward and bring in more data and have this online, the dimensions that we view the map through can obviously change. And then, like I said, I want to show you like this first batch of people that we actually in the community, Jonathan or Shai or me, had a chance to talk to and to kind of get to know and talk to them about what they're doing and then try and place them on the map. I will say, again, it's not easy. Especially in the academia, people are connected to other people and doing many things, and kind of pinpointing them on one place on the map, I think, is a disservice. I still did it, so I think that going forward, this needs to be a bit broader. So here's the map. And I'll go over the paradigms quickly. Quantum circuits, again, I'm everything here I'm going to do very high level because A, I'm not a scientist, and B, I think the heterogeneity of the audience means that some people know this and are not going to get any benefit, and others are not going to understand from this 60 seconds that I'm going to talk about. But idea behind quantum circuits is that you have Boolean gates that work on a quantum information space. So you have something called the qubit that can be 1 and 0 superpositioned of ones and zeros. And then you have gate logic that works on those qubits to yield the result. IBM Q, Google Bristlecone, Intel, something like Tango Lake. And these are machines that are out there. They are computers. There's kind of no argument about them being computers. Okay, yeah, I'm sorry. Second paradigm is adiabatic systems. The term is a little questionable. Is it adiabatic? Some of it are annealers. Some of it are photonic based. So the idea is a system that has a rigid structure, and then you provide it with some kind of a set of values, and it evolves based on its structure and provides an answer. So it's not exactly a classic computer. It doesn't have gates, but you can still achieve some kind of computation with it. I always, if this is the ENIAC, the early computers of the 1940s, this is the calculators that IBM used to make. So it seems to have value, but it's not exactly a computer. So it's a different paradigm. These two paradigms are kind of at odds with each other, especially in the academia. I think they both have a lot of prospects. And then quantum communication is kind of two things. It's either the ability to transfer quantum information from point A to point B and hold or maintain the quantum state of the information, or something completely different, which is using quantum technologies to transfer classic information. Or maybe make it more secure or making it more coherent, but the information itself is classic, but this is kind of under quantum communication. Lots of communication companies are obviously involved in this. And then quantum sensing, which is the field of actually using quantum effects and quantum technologies to make better sensors, better measurements, higher resolutions, things that we couldn't have done with classic systems. Obviously, both quantum sensing and quantum communication influence and affect and improve and enable quantum machines like quantum circuits and adiabatic machines, but they're kind of a different paradigm in terms of the research that's being done. And then there's lots of stuff here that is going to be, I think, empty, but again, going online and bringing all the data in, there's lots of stuff that still is relevant, like topological systems. Actually, I have one person here, and quantum memory and registers, and lots of stuff that's not in those four. And then going quickly over the layers. So hardware, by hardware, I mean actual machines, computers, machines that are like coherent system, like built systems, integrated systems that provide some kind of output. So obviously quantum computers are going to be in this category. The next one is infrastructure, and that includes physical and logical. So hardware components that are used for improving or enabling quantum computers, as well as software mechanisms and things that are very, very low level that are there to kind of aid in the let's say the coherency of the system or some aspect of the system. Over that, there's algorithms. Algorithms here has a very specific meaning. These are not classical algorithms, but this is a way to represent problems so that quantum machines can understand them and yield some kind of result. Specifically on quantum circuits, maybe some of you on the non-technical side or non-academic side have heard of Shor's algorithm, Grover's algorithm. So these are like these complicated mathematical formulas that enable us to represent problems in a way that can be presented to a quantum machine. And then others, again, and there's lots of others here. Obviously, there are not a lot of solution providers, not a lot of software companies today, but I felt like, again, as time progresses, I think we will see more things coming on the top layers and the top layers being formed. So now we have a better, I guess, map, and I'm going to kind of start going through people to show you kind of how we want to do this. Like I said, the people I'm going to show you are people that we've met and talked to and kind of tried to figure out what they do and where they belong. This list is very incomplete. It's not in any kind of order of importance or anything. It's just people. First person is Roy Ozeri. He's a professor at Weizmann. By the way, I'm gonna do a huge disservice to everybody on this list because they do so many things. I'm just gonna kind of talk about one thing they do and stick them on the map and move forward. Okay, I'm kind of out of time. Roy Ozeri is at the Weizmann Institute. He is working on building quantum computers that are based on trapping atoms, electrically charged ions, and then cooling them down, and then basically putting them into specific quantum states and entangling them with each other and measuring them. So he's going to go here, right? So he's building hardware, a computer, and he's using the paradigm that he's using for his computer is a quantum circuit paradigm. So he has gates that you can run on the on those qubits. Next person, it's terrible. Satat from the Ben-Gurion University. We have Ron Fullman here. You're not on the board, by the way. You can put yourself, but you probably know him. So he's working, and again, I might be completely wrong, but he's working on quantum cryptography, quantum currency, and the idea behind how classic complexity theory kind of coincide with quantum ones, and creating quantum algorithms mostly for quantum circuits. So I have to say that he's like here and here as well, because a lot of the stuff he does actually has a lot of relevance for quantum communication. But again, I pinpointed him, but he's definitely working on the algorithm section. Maybe he should have like another appearance down there. Quant Li, so sadly, I think they're not here because they have a conference today in Jerusalem. They're a company that is in Jerusalem. They provide quantum key distribution services through machines that use quantum effect to create those keys, and they would be kind of here. So again, they are providing both actual machines that do the quantum key distributions as well as components for machines. So they're like half and half. One more. Again, huge disservice. This person does so much. He he's a trove of information, and he's just has his hand in so many things. But specifically, I think maybe what he would have liked to be mentioned for is that he's working on something called Josephson Junction qubits, which are a specific type of superconducting circuit that is used to store information. He's working on the improvement of those qubits. He's trying to understand how they react when interacted with, and make them less prone to fluctuation and more exact. And again, he's going to be here because he's not building a computer, but he's building infrastructure. Although the research that Nadav Katz does, even with Josephson Junction, is definitely going to be relevant for adiabatic systems, specifically DWave, which has an adiabatic system, runs on a superconducting circuit. So, but most of the stuff he does now is being tested through quantum circuit as a paradigm. So that's why he's up there. Lights over. Hey, we're here. Hi, Chen. So Chen Trondonsky and Ruti Ben Shlomi, they are building a computer, a computation machine. Like I said, in this adiabatic, I hope that's an okay description, based on a laser cavity that, again, has some kind of structure, receives information, processes it very, very fast, and returns an answer. So they are going to be here. I hope that it's okay. I think the name adiabatic is problematic, but I think that you're happy to be in the same category as DWave and the entity Docomo. So that's that. And sorry. Next person, Shai Georgi, a professor at the Technion. Again, UNC service does so many things. Specifically, we talked to him again about his work on superconducting circuits. And we talked to him about the stuff that he does. He's focusing on figuring out new gates. So kind of understanding how to approach those qubits and what kind of interaction can be created with them to put them in all sorts of interesting positions or superpositions. So he's going to be in the same category as Nadav Katz, and this category is actually going to be pretty full. I don't have many more, don't worry, but going forward, I think that quantum communication and infrastructure for quantum circuits is a relatively flourishing field in Israel. Nir Bar-Gil, completely different category. This person uses nitrogen vacancies in diamonds. So diamonds have this kind of flaw in them, and this flaw can be used to create a quantum information space. This actually, there are ideas on how to use this as a computer. Nir Bar-Gil specifically uses this to create sensors, versions of MRI. So he's going here under sensing and infrastructure. He's not building machine. He's just researching and studying and experimenting on these nitrogen vacancies. Quantum machines, kind of like the first, biggest, most known Israeli quantum computing startup. They are building, and by the way, I'm sorry if I'm running. I really want the interesting guys to come up here. So I'm kind of showing you what this is kind of going to look like. So I'm sorry if I'm kind of rushing forward. So quantum machines are developing controllers. So what they want to do is they want to provide an abstraction layer for quantum computers. So if you're building a quantum computer, you don't have to build the controller. The controller is going to be the thing that actually translates your classical commands like run the Hadamard gate into a set of interactions with the machines, which are analog, usually like RF or some kind of electrical pulse. And they're creating the actual controller, which is a physical thing that they want to connect to the machine. So here they are also in the same same square under infrastructure and quantum circuits. And I think Adi's last. Yes, okay. So Adi Stern, very interesting person. Also, this is terrible because he does so many things, but specifically I wanted to mention him and put him on the map because he's doing something very interesting. He's doing something which is going to be on the other there. So he's working on the idea of creating topological states of matter where quantum coherence can be maintained for longer periods of time. There's a question of whether it works or not, but I think that's it. So this is yeah. So again, like I said, the idea was to present to you kind of what the goal is, and the goal is to have at least about 100, 120 people put into that database, tagged, categorized, and then making the connections between the people, which is very important, which is not presented here, so that we can start to extract some value from that. We can start kind of understanding where there is value and you know who needs help or who has help to offer. So I think that's kind of it, and we're going to skip the break, I think, right? Because we want to really dive into the Q&A session. Thank you.